So we are in the last chapter. We'll be doing chapter 13 and then we'll be done for the semester. Linear regression and correlation. So linear regression and correlation involves studying more than one variable. So somebody may be interested in figuring out, let's say, height versus like arm span, fingertip to fingertip, what is the length, and you may plot that on a scatter plot. When we make a scatter plot, the variable that we want to predict or estimate goes on the y-axis, and the variable that we are using to estimate the other variable goes on x-axis. So suppose somebody is interested in figuring out, given height in centimeters, so for a given height, what is the arm span in centimeters? So to find if they are related or not, the best way is to make a plot. So any linear regression or correlation study always starts with scatter plot. The reason is, this method is called linear regression, and we can use linear method only when two variables are related in a linear manner. So if we plot these two variables, and let's say for one person we get this value, for some height that's the given arm span. Then you collect data on another person, it looks like this. Then you have something like this. I'm just making up this data. I don't know what's the reality. So suppose you get this kind of pattern. So you can see that relation between height and arm span more or less seems to be a linear kind of pattern. So as height increases, as height goes up, values of arm span also go up as per this scatter plot. We may be able to draw a straight line passing through these data points, and that could become our linear regression model for estimating, given a height, what is the arm span. So once we have this equation, that equation can be used. So this equation is equation of a straight line, y equals b0 plus b1x. So this is the equation of a straight line that you might have seen actually starting from middle school. So this b0 is y-intercept. So y-intercept means if you extend this line, where that line will cut y-axis, that point is b0. And then b1 is the slope. And developing a linear regression model basically involves estimating these two, and there's a standard formula that we can use and estimate b0, b1. So usually people make a mistake when they do linear regression, and that mistake is they don't plot the scatter plot and then directly go to this formula and find equation of a straight line. But that straight line will not be valid if the relation is not linear. So instead of straight line, if it was like a curve, then it would have been incorrect to use that method to predict other variable from x variable. We'll do a team activity, something hands-on. You will be collecting data. Number one, measure height and arm span of each team member in centimeters. So fingertip to fingertip. So you'll have to find a way to measure everyone. And the only tool that I have is this. So you'll have to find a creative way to use this. Each team will get 3 data points, 3 heights, 3 arm spans. So one means this height and that arm span is for that same person. So you cannot mix them up. And then once you complete that, then number 2, we will compile the data from all the teams. So we'll get data from the entire class and use that as our data set. A is explain relationship between height and arm span based on scatter plot. And then I'll help you to get slope and y-intercept so that you can write your equation of a straight line. So using that equation, you will make 3 predictions. Yeah.
Okay, chill. Oh, I think we just over here. Sounds crazy, man.
Okay, so I will go to Posit Cloud and log in using my Google account. We'll open a new file, first one, and save that as chapter 13. And once I have that, I'm going to clean everything up, close previous chapter. So all our class files are here. Let me call height as h, and we'll save data there. Similarly, for arm span, I'll use A and save data there. Let's start from here. Your 3 values for height and arm span. So I'm going to run this and run this so that these 2 data points are recorded. We have 19 data points on 19 students. To make a scatter plot, we use a function called plot, plot. And we want to plot arm span on the y-axis because that's what we want to predict. That's the last item you have to do. Using height, you have to predict what is arm span. So whatever you are predicting, that's called dependent variable. So we are saying that the arm span is dependent on height of a person. So height will go on x-axis, arm span goes on y-axis. Plot x comma y, whatever you put first, that will go on x-axis. So our height is in h, arm span is in a, and when you run that, you get a scatter plot. So clearly, we see as we go up from 160, 165, 170, 175 to 190, data points are going up. We never get a perfect straight line trend. It's not that every data point in a linear regression will fall exactly on a straight line. That never happens. There's always variability. So there's no reason to believe that it's not a linear relation. So to estimate now intercept and slope, let's call our model or linear regression model simply model. So we'll store results in this model, and we are going to do LM, linear model, and we are studying one variable versus the other, arm span, and then tilde sign and h. Arm span is a function of height. So you run that, and then if you do summary of the model, all the results are actually stored in model. So I'm going to do a summary to get things out. So this is what we get if I run summary. So it may give a lot of information, but the key thing is intercept is this and slope is this. So using these two, you should be able to write your equation. And then plus the slope 1.5 something times height. So that becomes our straight line equation. You can use this equation to estimate if height is 160, then what is going to be your arm span. So you plug in 160 here, so 160 times this, and then you add intercept and you get a prediction. So what we are doing is plus 1.5 something times 160. So that gives you 141.3. Similarly, if you put 175, you get 164.4. Similarly, if you put 85, you get 179.9. Thank you. You can take a picture if you need a copy. So let's look at some examples. So when you plot two variables, let's say your variables are amount of time you spend on gaming hours, and skill level, basically may be captured in different ways, like how many levels or how many points, things like that. And if you make a plot, scatter plot, and if it is something like this, so that the pattern can be captured by a straight line equation, so that's what we call linear relationship. We may also have a situation like this. So coffee consumption versus productivity. And if you somehow capture that and you get a plot like this, like initially it improves productivity, but then reaches a peak, and after that, if you have more coffee, probably productivity comes down. So clearly this is not a linear relationship. It looks like this. This is still a relationship between two variables. The only thing is it is not linear, so we can call this non-linear. So there are several methods that deal with non-linear relationship also, but in this chapter we only focus on linear relationship because that's the title, Linear Regression and Correlation. We do not look into non-linear relationships. So when you plot scatter plots, let's say you have two variables, social media posts versus number of likes. So more posts and you count total likes, so they are likely to go up together. So that's a linear kind of relationship. So this kind of relationship we call positive because the slope is going in the positive direction. One variable increases if other variable also increases. So that's a positive relationship. Another example of positive relation can be number of steps you walk in a day and number of calories you burn. But sometimes you may also have relations like these, where you plot two variables. So let's say on x-axis you have temperature, like outside temperature, and y-axis you have hot chocolate sales. So that may be something like this that can be captured using a straight line relation, but it is in the negative direction. So one goes up, other falls down. So that is called negative linear relationship. Another example could be if you drive your car at higher miles per hour, you may get less mileage out of it. So that is likely to be a negative relation. So before this chapter, we have never covered that kind of situation where you have two variables and you are studying relation between two variables. All the other situations were, you can call univariate. Univariate means one variable before, you can say, chapter 13. So all were univariate cases. Now we are talking about two variables. So that's what is called bivariate. Bi means two. So we are looking at situations where you have two data points, like temperature, chocolate sales. Social media post, likes. So you are counting that. So you are getting two values. If you plot two variables, x and y, there is a possibility of getting this type of plot also. Almost like a zero. So if we get this pattern, we call this as a situation where we have no relationship. So you can have positive, negative, no relation, also like non-linear. So in all these situations, there is a variable called x that goes on x-axis, and that variable is termed as an independent variable. And variable on the y-axis or y variable is called dependent variable. Because in this relationship we are studying whether y depends on x or not. So gaming hours is an independent variable and skill depends on that. How much time you spend gaming, so skill level will change as per that. Because skill depends on this, that's a dependent variable. Similarly, how many likes you get, it depends on how many social media posts you make. So like is a dependent variable and social media post is an independent variable. How much hot chocolate sales we get depends on temperature. So temperature is independent and sales is dependent variable. So we always use those two terms. Sometimes independent variables may just be called x variable or input variable, and dependent variable sometimes people call response variable, but these are most common names. There is also something called spurious correlation. So when we study relation between two variables, we should not be surprised when we make a scatter plot. If you make X number of social media posts and how many likes you get, and if you see it is increasing, that should not come as a surprise, because more of this will lead to more of this. But what we are studying is whether that relation is linear or not, and other thing we are looking at is whether that relationship is strong or not. So one is whether it is linear, other is what is the strength of the relation. We are not doubting that if you make more social media posts, you will get more likes. There should not be any doubt about that. The only thing we are checking is strength of relation and whether it is linear. So you cannot simply like plot two variables and call that as a correlation or relation between x and y. So suppose you have a x variable. So suppose you have two variables. How many TikTok videos people post on a given day, and what is the amount of rainfall you get in Boston. You plot these two and you get this pattern, and it looks like a linear pattern. So now we cannot say that we are getting more rain in Boston simply because people are posting more TikTok videos. We cannot claim that, right? Because there is no connection between these two variables. It just happens that when you plot it on a scatter plot, it looks like a linear relation, doesn't mean that they are related. So that's what is called spurious correlation. Two variables may go in the same direction for some other reason, but we cannot conclude that this is causing that. Unlike these situations where we know that these two are directly connected with each other. So that's what we need to be careful about. When we have a scatter plot like this, and you have two variables x and y, you plot and you get this data, and then you draw a straight line. So this straight line equation you have seen is given by y equals b0 plus b1x. So this is the equation of that straight line, where this b0 is called y-intercept. So this is called y-intercept because if you extend this line, it will intercept y-axis at this point. So this height is b0. Similarly, b1 is called slope. So if you have like x and y and this as a straight line, then your slope is likely to be greater than 0, positive. But if you have a line like this, your slope is going to be negative, less than 0. Or if your straight line is flat, parallel to x-axis, then slope is 0. So slope is basically that line and how steep or how flat it is, and also the direction of relation between two variables. So you may have x and y and this kind of relation. You may have x and y, but now data points are much closer to straight line, or you may have where you have data points fall exactly on the straight line. All the data points are exactly on the straight line. So we can call first one as weak positive relationship. Second one is strong. And third one is called perfect. No deviation from the straight line means perfect relation. You cannot have anything better than that. But it is theoretical, like in real life we don't get that kind of relationship. So when we are studying this relationship between two variables, and we may have these data points, and suppose your average of y values is somewhere here, y bar. So there are a lot of things going on here. One is this straight line and how far each point is from the average, so that is one. So you can say this variability, and then there is a variability from the line to y bar, this variability, and then there is a one from here to here. So there are three types of variabilities. So we capture the total variability using SST, and then there is one part which is SSR and other one is SSE. So total variability, SST means sum of squares total, which means total variability in the data. SSR means sum of squares due to regression. SSE means sum of squares due to error. So there are three types of variabilities, and the total actually is broken into two parts. How far each data point varies from y bar, so that captures actually SST, total variability. How far this red one, so how far that y bar is from the line, so that captures SSR, and this one is SSE. Like somebody may say, for a given value of x, we have this data point where y is a value, and at the same, almost same, there's another data point, but the y value is very high. So why that variability? So that goes into error. So sum of squares due to error captures unknown variabilities where we cannot explain anything. In a way, you can say this is like explained variability, explained part, and this is unexplained part within the total variability. In statistics, when you see error, basically it is something that we cannot explain. It is unexplained part of the variability. Using these two, we calculate what is called coefficient of determination, which is given by R square equals SSR divided by SST. SSR divided by the total variability. So out of total variability, how much is being contributed by your model, basically, regression model? So that is captured by R square. Obviously, sum of squares due to regression cannot be more than the total, because this is total and this plus this is the total, so this has to be less than this. So SSR is always going to be less than or equal to SST, which means R square, the maximum value for R square is likely to be 1. R square is usually between 0 and 1. 0 because it cannot be negative. It's a square, you cannot get a negative value. But it cannot be more than 1 because SSR cannot be more than SST. When error is missing, sum of squares due to error, if it is 0, if that entire part is gone, then this is equal to this, which means this is equal to this, R square will be 1. So that situation is like this. You have a scatter plot between x and y, and your data points are exactly on the straight line, no error, so R square will be 1. Coefficient of determination, so 100% of the variability is being explained by this kind of model. There's another thing called correlation coefficient. This is small r sine of slope times square root of R square. So basically, if slope is negative, then R value will be negative. R lies between -1 and +1. You cannot get a value more than 1, you cannot get a value less than 1. So if you have a scatter plot like this, and if you have a scatter plot like this, where data points are exactly on the straight line, so that's a perfect relation between x and y, but one is positive, other is negative. So your R square in both cases will be 1 because there is no error, but your R is +1 here and R is -1 here. Now let me go back to that data. So the data that we collected, height versus arm span, we ran this and we made a scatter plot, and the scatter plot looked like this. So you can see like two people have almost same height but different arm spans. If you look at this point, slightly over 175, there are 4 students, but they have very different arm spans. One variability is as h increases, A also increases. So that is the explained part, that when height goes up, arm span goes up. But unexplained part is why this variability, so that we cannot explain from this data. There may be some other reasons, but this data cannot explain that. So that is the error part. For this scatter plot, once we confirm this is a linear pattern, then we created a linear model using LM. And then if you look at the model, this is what we had. So it gives you output. Residual means errors. So from the line, how far above and below. But we are usually interested in coefficients. So we got B0 and B1. And this table also tells other things. It uses t-distribution, but the most important thing is p-value. So p-value is quite less, and that's why there are 3 stars. So even if you are looking at 95% confidence level, you can easily conclude that height is a very important variable in having an impact on arm span. So this is a statistically significant variable. That's what you can conclude with 95% confidence. You have R square, multiple R square. So R square is 0.7855. So that's the coefficient of determination. Once you have R square, you can take square root of that, or you can use a function COR, correlation between H and A. So that is about 0.886. And because it is a positive relation, that's why it is a positive value. For this data, we can write down. So what is the interpretation of this? What does it mean? So I'm rounding this to about 79%. About 79% of the variability about 79% of the variability in arm span is explained by the linear relation between height and arm span. So that model explains about 79% of variation. So once you have R square, you can calculate R very easily. That was correlation coefficient. So we'll look at actually one example. Shop owner uses straight line regression to estimate number of ice cream cones that would be sold in a day based on temperature. So owner has data for 2-year period. So you have this data, temperature and ice cream cones sold. One question is, which one of these 2 variables is a dependent variable? Yeah. Ice cream cones sold, because that will depend on temperature. So temperature is independent variable. So this is X. You should plot this on X-axis, and this is Y. Should always go on Y-axis. Temperature, small t. And we can use C for cones. So this is given by us. This is an object that we can call anything. We can call it temperature also, temperature. And this could be cones. 70, 85, 65. So this is the data we have. So we run these 2 lines. And before we use linear model, we should always check whether they are really linear or not. So we plot this. On x-axis we want temperature, this one, comma, cones. And then you run. So this is what we get. When you are looking at a scatter plot, try to have a square picture, because if you make it flat like this and conclude that it's almost flat, so that will be misleading. Or if you make it like vertical, then even small relationships will look like very strong. So always look for a square. So clearly, as temperature goes up, more ice cream cones are getting sold. And there's no reason to believe that this is not a linear relation. It will never be perfect, but it's more or less on a straight line pattern. We can create a model. Cones will go on y-axis versus the tilde sign and temperature. But we can also save this something like model and then look at summary to get more information. Summary of the model. So intercept is negative 567.47. This is slope 9.7. What is the meaning of this 9.7? So that's the slope of the line, but what does it mean? So if temperature changes by 1 degree up or down, so because relation is positive, so if it goes up by 1, then this shop will sell 10 more ice creams or ice cream cones. If temperature falls by 1 degree, then 10 less sales. So demand will go down by 10. R square is 95%. Plus times temperature. So that's the equation of the straight line. After confirming through scatter plot that relation between these two variables is linear, B1 or slope equals 9.7787. Temperature changes by 1 up or down, sales will change by about 10. Because this is number of ice creams, so instead of using 9.77, we can round it to 10. R square is equal to 0.95. It means about 95% of the variability in ice cream sales is explained by linear relationship between temperature and so that's what R square means. That how much of the variability is the explained part, 95%, and remaining 5% we don't know. There may be so many different reasons for that. But one reason, which is temperature, is contributing 95%. So that's obviously a big part of that. This is the last lap and you should finish strong. I will try to connect with some of you, like whoever is interested on LinkedIn. When you add your skill levels, data analytics or R programming that you have done in this class, so I will endorse your skills by going to your profile if you are connected. So look out for that. And I think we had a good class.